go. Okay, so as she said, I'm Jesse Codling, presenting on behalf of a whole bunch of co-authors, Jeff, Tim, Jiale, Pei, and I, all at University of Michigan, Hugo at Cisco, and Young and Yiwen from Stanford University, and presenting our work FloHR, where we detect human heart rate at a distance away from a seated person using floor vibrations. So why do we care about heart rate so much? So imagine you go to the doctor, maybe you think you're sick, and what's the first thing they do? They're going to check your temperature, possibly blood pressure, definitely pulse oxygen, and along with that, heart rate. It's so much of a basic metric for human health that it drives a almost $33 billion industry. And we particularly are interested in this ubiquitous or continuous monitoring for two reasons. One is to get baseline health, and also to look for abnormalities and anomalies, because sudden changes in heart rate are a very early warning sign of problems going on in the body. So how should we do this? Well, the most obvious is you can do it manually. You can stick a finger on your wrist or your neck, or a doctor might use a stethoscope and listen to your chest. I would call that pretty ubiquitous. I'm pretty sure all of us, as long as you have hands, can put a finger to your neck. But it's very sporadic, not very precise. It's hard to get a baseline measurement that way. So a lot of work, especially now with a lot of products that are coming out with these wearable devices, thinking, yeah, that's much more continuous and accurate, but imagine instead of you, the engineer, we're trying to monitor your grandmother, or a kid who's been in and out of the hospital, and they have all these devices all over them for so long. Now they have to keep this thing and remember to charge it and wear it, and a lot. Problem. So next step away is, well, why don't we use something ambient? Why don't we use a camera or something radio-based, or Wi-Fi, or something like that? Well, that can be continuous, accuracy mixed, but then you need line of sight, and might have privacy problems. I certainly don't want a camera in my bathroom. So we had this thought, and we've seen some previous work in our lab before, looking at the vibration from heartbeats. So when that stethoscope is on your chest, they listen to your heartbeat, right? Well, what they're listening to is the vibration, the movement inside your body turned into sound. So we have vibration inside the body. Hope you can see that. And when you're sitting down, vibration in the body is going to move into the chair, move out. The thought then is, well, vibration in the chair, that should keep moving down the chair into the floor. So first big question, if we listen to the floor, can we hear your heartbeat? Could be really great if we can. That could solve a lot of the challenges from the previous approaches. So let's give it a shot. We'll can use a pulse oximeter, something directly touching the body for ground truth. Of course that works. We knew that would work. And we'll put our standard piezo accelerometer on the chair, and I don't know about you, but I don't see anything there. And if we move the sensor farther away onto the floor, out to 2 meters away, still nothing. To put it in perspective, the signal that is plotted there is actually something there. It's about 100 micro-G at most. So good luck with the accelerometer. But in our lab, we've done a lot of work with geophones. We can pick up footsteps at 20 feet away. Or we can, say, figure out if somebody's washing their hands. Thank you to our general chair for noticing that at one point. But to pick up something so tiny like a heartbeat, you still need to do some changes to the hardware. We need more dynamic range. We need to be able to adjust the gain and turn it way up so we can pick up a heartbeat. And we need to reduce the noise. So this is both things on the board, like the communication, the power circuitry, and outside noise, where we've got all these electronics around us. There's noise from the power, and details in the paper, but the key idea is we know some things about how the floor responds. We know things about the general frequency response of a floor and of the geophone, and putting that together, that can give us some ranges where noises more okay, and where it's less okay. Doing all of this, we reduced the baseline noise for our geophone sensors by four times. Comparing it with an older platform that we used in our lab before, we saw a 6 dB decrease in baseline noise. Details in the paper and now open source as well. So, accelerometer, not going to work. But switching to the geophone-based platform, the pulse oximeter, we knew that was going to work. And then with the geophone on the chair, well, that looks like a pulse to me. Maybe not quite the same shape, but there's definitely something happening at the right time. And even as the sensor, need to watch my hands, even as the sensor gets farther away from the person, onto the floor, 2 meters away, we see something still. Clearly, even though the peak, the pulse is getting smaller and spreading out, we can still see the heartbeat, your heartbeat, on the floor 2 meters away. But the no free lunch is going to come to bite us still. This vibration is still so tiny that if you touch the floor, you won't feel it. And there's a lot of noise. Lots of things create vibration. So we classify the noises into 2 types so we can do something about it. Short-term noise, this is things like footsteps far away or somebody tapping on the phone. We found that that's really, really close in amplitude to heartbeats. And then we have longer-term noise, something much longer than a heartbeat, like the plumbing or the HVAC or appliances or talking. And that'll just generally raise the noise floor. And on top of all of that, we have our wonderful friend dispersion, because floors and chairs are made of things like plastic and wood and metal and stone if you're lucky. But all of those are going to spread the pulse out further. So we'll do some engineering, we'll build a system, and start with the low noise sensing hardware we talked about. First step is we need to do some filtering specific to the heartbeats to try to bring that spread out signal back together. And then peak detection, very conventional, figure out where is the heartbeat, including trying to throw out things that are obviously not a heartbeat. If you have a footstep that's going to be an order of magnitude stronger than your heartbeat, we can throw that away. We know that's not a heartbeat. And then to find the heart rate, we look for a pattern of periodic events. So the short-term noise is going to create some false positives, maybe occasionally mask the true positive, the true heartbeat. And so, but heartbeats are about periodic in a short time. And so if we look for that periodic events, the short-term noise is not going to be lined up. It's going to be out of phase. So if we find that periodicity, we find the heart rate. And then we still have long-term noise. Sometimes we just can't see the heart rate. We can't see the heartbeats. So what we do is we take some features from the heartbeat detection, the peak detection, the movement detection, about the noise, and try to estimate how well are we detecting heartbeats in the first place. The thought then is, if we know when we can't detect heart rate, then we can just ignore it. We say, oh, we got a heart rate, but this one's really bad, so I'm just gonna not tell you until later. For those 3 problems I mentioned before, this first block works on the dispersion problem, then periodicity for the short-term noise, and the confidence estimator for long-term noise. For the sake of time, details of course are in the paper, but I'm going to just go into some detail about the pulse shape filtering. So what's the goal of this filter? We want to reduce noise and emphasize the heartbeat. So of course, let's use a matched filter, right? Well, that matched filter would need to depend on both the floor structure, which is inhomogeneous, and on the individual person's physiology. The exact shape of your blood vessels and your heart changes the shape of your pulse signal slightly. But pulses are wavelet-like. When working with an EKG or a pulse oximeter, we often use a Ricker wavelet, the bump, right? Well, on the floor, we don't just have the bump. We have the bump and the elastic response of that bump. So instead of Ricker wavelet or second-order Gaussian, we'll use first-order Gaussian, which gives us both the pulse and the elastic response of the floor. One last challenge still, though. is what scale of the wavelet to use. Since, again, it depends on the individual person, and we want to be able to work with more than one person at a time, we use a bank of wavelet filters. So we take a whole bunch of frequencies, define the range defined by the floor, and sum them all together. So let's take this and evaluate it. We went to an actual home. We had 10 different people, younger and more distinguished. We had male and female, varying states of health. We had them do some light exercise just to get their heart rate up and then rest on a chair on a hardwood floor for 10 or 20 minutes. We used an optical PPG sensor. I will definitely mess that up if I try to say it out, but same thing as a pulse oximeter, either on the ear or on the finger. You can see those in the photos. And then the same 3 sensors we talked about, one on the chair, one right below the chair on the floor, and one 2 meters away. And since we did not recruit 10 monks for this, we do have some noise. People talked, people played with their phones, somebody was using the bathroom, so the toilet flushed, so there was noise to deal with. So our results come in. We've got the y-axis here is the mean absolute heart rate error. X-axis is sensor location. The first bar is using FloHR's hardware, but a conventional heart rate detection algorithm without the noise handling. Then adding in periodicity matching, and finally the confidence estimation to reject low confidence heart rates. In total, we see our noise handling algorithms reduce the error in detected heart rate, and gives us similar accuracy to wearables, about 7 beats per minute on average, when we're nearby, so on the chair or on the floor. Farther away, at 2 meters, we get an average heart rate error of 10 beats per minute. Looking across different people, well, again, for most people, we can get similar accuracy to a wearable. However, there is some variation. So if we look, we particularly notice person 2 here. Again, y-axis is now median error, x-axis is different people. And person 2 told us after we got their vibration data that they have a heart condition. So instead of the valves opening nicely like they do on most people, they kind of flop around a bit. And that means that his vibration signal looks very different to a normal person. And so we missed a lot more of his heartbeats. The accuracy is not as good. However, even in this really difficult case, we still see a median heart rate error below 12 beats per minute. In conclusion, FloHR is able to detect heart rate from seated people at a distance of 2 meters so far, using floor vibrations. We evaluated with 10 different people and saw an average 10 beats per minute heart rate error at that 2 meters of distance. While accuracy does vary with people, we actually can see some physiological reasons for those differences as well. Thank you very much, and I'm happy to take your questions.
Don't even have to ask.
So my name is Tushar Raut. I'm from University of Virginia. So I have 2 questions for you. To the best of my knowledge, the power consumption of these geophones is on milliwatt range. Am I right? So how can you use this technique for long-term heart monitoring? Number 1. And number 2 is that they are not super cheap, as I know. So how you can make them universal technique?
Yes, so it sounds like there was kind of 2 questions in regard to long-term and continuous monitoring, but one with cost and one with power consumption. So as far as power consumption, the geophone itself doesn't technically consume power. The power is consumed in the amplifier and the conversion circuitry, but with using the hardware platform that we've developed, not in the heart rate case specifically, but we've been able to run them off of a lithium battery for about 24 hours at a time. For anything longer term, just running them off of mains, they do not draw a lot of power. So in the case, for the heart rate case, typically I would think we would just run it off of mains, because the idea is you just need one of these for a room, as opposed to needing like several on all of the chairs or per person. It's install it in the room and you're good. To the cost question, again, that That's mostly an issue for right now where it's a very research-oriented device. If we were to commercialize something like this, economies of scale can bring it down much farther. So our current geophones cost us maybe $20, $25 US per unit, but I already know that we could get them much cheaper if we were to get them out of Shenzhen somewhere for cents each. Anyone else?
Yes. So thanks for this nice presentation. I had a query or could be your future work kind of thing. So the thing is that your experiment is purely a controlled environment. Your floor were there, but when I talk about the floor type, when floor is wet or dry, different conditions may occur. And suppose two persons are sitting side by side on two different chairs, so that could be a challenging for you. So how you will address such challenge?
Yes, so I believe, again, there were kind of two parts to that, one with differing floor types and conditions, and one with multiple people. So multiple people that is an excellent question. That is a real challenge right now. So one way that I would think would help with that, as opposed to our kind of wavelet bank approach where we're trying to create a generic filter for an average person, it would be to try to create a template per person, at which point you'd be able to differentiate heartbeats by which person they are, which filter they're responding to. Creating that template would mean then you'd have to do some modeling of the individual person and the differing structures in between in order to generalize it. Across different like floor types and floor materials, we did definitely notice that we worked in a hardwood floor as a proof of concept, because at the start we weren't sure we could even pick up the heartbeat at all. Obviously, hard floor is going to be easiest. The more padding and kind of the more absorptive material you have, the lower the amplitude of the heartbeats is going to be, which generally translates to less range. So say in this room, I probably can't do 2 meters, but hopefully we can still do under the chair. That would be something interesting to see.
Okay, one last quick question. So for how long I have to sit on the chair?
How long do you have to sit on the chair for?
I think our longest time to getting like a good heart rate from someone was about 5 minutes, but that was a particularly fidgety person who may or may not be standing in the back right now. So.
Okay, thanks.
Yes. Yeah, on average it's much shorter.
Yeah, so one more question I have is, I'm not a medical doctor at all. I would imagine, though, to capture sort of someone's full heart health, you would want to be capturing it under different types of conditions, right? Mm-hmm. Going for a run, going for a hike, swimming, walking. Would you be able to capture all that just sitting on the chair, or would they have to put on a Fitbit to get their heart rate under these varying conditions?
Yeah, so the question really, thank you for that question, really relates to like different kinds of activities and whether like just sitting very still is going to work. And that's where part of that is kind of the job of this long-term noise thing, because when you're moving a lot more, just your movement itself is going to produce a lot more vibration than your heartbeat does. So just purely like while walking, I think it's unlikely we'll be able to make that work. But the trick is you don't move constantly. So even when walking, say, you might take a rest and stand still for a couple moments, and during that couple moments, that's when we can pick up your heart rate. Also, just standing posture in general does create a bigger challenge because your feet are much smaller than your butt, and just the smaller contact area means less vibration is transferred into the structure.
Awesome. Thank you so much for the great presentation.
Thank you.